Welcome to First Tuesday. It's the first Tuesday in April. I guess welcome to spring to everyone. Very nice looking day today. Haven't been out there yet, but it looks very pleasant. I'll introduce our speakers in a second, but just to make sure that everyone knows that the next First Tuesday will be Nathan Mikowski. And the date will pop up here in a second on the screen. May 4th. If you would like to present, June 1st is wide open. So please volunteer, send your name to Cheryl Dudek. Since it's up here, Monica Perez will be our May NP speaker. And we have a couple of behind the science activities. One on April 20th and one on May 18th, as you see there. So one's on device design and one is on what the media wants to know. So we have a number of things happening. Okay, so let's see. Will the stars of the show pop up here next? We seem to be stuck on. Oh, there we go. Nope, not yet. There they are. So today we have Aasef Shaikh, Fatema, Ghasia, and I'm gonna try your name, Palak Gupta. Is that close or okay at least? All right, thank you. I usually look these things up beforehand, and my day's been completely full, and I thought, oops. So I'll take a try. So I think Aasef is going to start. Is that right?
Yes. So
now that you're caffeinated.
I did not, but whenever it comes to eye movements, I automatically get caffeine, so I'm good.
Okay.
I did not get coffee. I forgot actually. So let me. Am I able to share? I should be able to share, right? Oh, great. Maybe. Okay, this is good. And then, okay, can you see the actual PowerPoint screen? Great. So today we will talk about something what we call, in our lingo, we call David Robinson style. So I don't know if everyone knows Dave Robinson. Dr. Kirsch, do you know him, right? So he's the father of our field. Do you want to say something about Robinson?
I interviewed with him when I was looking for graduate schools, just a FYI. That was a million years ago. I'm sure I see Pat Craig on here. You must have known David Robinson.
Yeah. So those who don't know David, unfortunately, David passed away in 2016. He means a lot to all of us. He trained two of my mentors who are my academic fathers. So in a way, David Robinson, who is my academic grandfather. David Robinson was an engineer, biomedical engineer in Wilmer Eye Institute at Johns Hopkins. And he trained two neurologists, David Z and John Lee, who became the pioneer of clinical eye movements. And Robinson, of course, was a pioneer of biomedical engineering in eye movements. And ever since that combo, the way our field works is, at least the field that I am more closely intertwined with works, is that we get a disease, we try to study disease with objective eye movement assessment, try to figure out what goes wrong that leads to those eye movement problems. Then we take help from what we call extension to clinician's mind, which is mathematical model. And those models, then the models come up with a priori hypotheses. And then we test those models a priori hypothesis in our patient. And then we try to figure out what can we do in the model to fix the problem that is in the model. And then once we have some idea, we try that out in patient. And then sometimes it works, sometimes it does not work. That's how medicine is. So this is what we call, this is how the field, like, Lee and Z and, my training with them and Robinson. This is how we have been doing this science over last close to 50 years. So what we are going to do something today is we are going to look at 3D gaze shifts in patients with Parkinson's disease. And this is a big problem. And I will tell you why. It's a big problem for two reasons. For patients, it's a big problem because it's very common. And for clinicians, it's a big problem because it's although very common, clinicians don't know about it. So, and they just like ignore the issue. So 3D gaze shift and eye movements, they lead to many important things. And the most important thing that they do is they prevent blurred vision and they prevent double vision. So if you see everything blurred or if you see anything double, that's actually really a big problem because it affects your quality of life. And when I go and tell that to our colleagues in clinical world or even like grant reviewers, once that happened to me, that I was complained that one second. Sorry, we have a spider problem. Go away. One second.
Sorry, it's springtime, so it's spider time in the house.
Start talking a bit about versions.
Yeah, I can. So
I will move forward the slide and you can just talk about this slide.
Yeah, so as Aasef was alluding, these visual symptoms are pretty common in Parkinson's, and most neurologists are not familiar with it. He mentioned blurred vision, double vision. It's because they have trouble converging, where moving their eyes simultaneously to fixate in different depths. And so because of this, it affects their quality of life, particularly for near work. So they experience difficulty in reading. This can also contribute to increased falls. So all of these collectively cause issues with their day-to-day activities. So I can't advance the slide, but as you can see, it's pretty common, about 1/3 to half of the people with Parkinson's, and it could be early Parkinson's as well, where they can have these issues. Okay. All right. Okay, so here's a schematic of the setup that we use in the lab, but basically what we're trying to measure is vergence, which is defined as your ability to focus on a target and presented in different depths. So when you look far away, your eyes display apart, so that's divergence. And then gradually the targets, as they get closer to you, your eyes turn in towards each other, and that's convergence. And the most common problem that we see in Parkinson's is convergence insufficiency, although they can also have some trouble with divergence. Okay. So here's our setup. We have LEDs that are placed at different distances, starting from 20 centimeters from the nose and then going out all the way to 244 centimeters. And we measure eye movements while they are tracking these different LEDs in different planes. Okay, I can go to the next one. Okay. All right, so it's been a while since I've looked at this plot, but basically here we have pooled all the trials. The target is this box step here, and controls are in purple, and we have pooled them. So the solid line here is the mean, and then we have the Parkinson's subjects, and we are plotting the gain, I believe, over here onto the right. So gain is basically if the target jumps, let's say 10 centimeters, and you'd expect a perfect movement, then your gain would be 1. If the gain is reduced, meaning that then that in that case, they have trouble with the task. So you can see here, to the right, you're plotting box plots for convergence and divergence. And convergence, the rate gain is reduced. It's about half in Parkinson's, which are the black box plots, compared to controls, where it's not quite close to 1, because even in age, so these are age match controls. So as we get older, our ability to do vergence at different distances is impaired compared to the younger subjects. So that's why it's not a perfect one. But you can see that both convergence and divergence are about 50% of what you'd expect in controls.
Okay. I will take over. I resolved the spider crisis. So so this is a big problem, because what happens as a neurologist in our clinic when we see these patients, a lot of times they come and tell us that I have a hard time seeing things. Things appear blurred. I have difficult time reading the book. A lot of times they have difficulty in focusing far to close nearby. And a lot of times, like people attribute that to aging, presbyopias, the prescription, dry eye, retinal issues, many things which can lead to visual problems. But really, in reality, a lot of times it may be a problem. I'm not saying that is not a problem, but this deficit is clearly something which contributes to this situation, this problem. So so in other words, as in the previous slide, we showed about 20% of patients with Parkinson's, their visual problems are attributed to inability to move two eyes in synchrony, which is a vergence deficit. So, but still these people can keep up with their day-to-day life, and they develop certain type of strategies to come across vergence. And so the convergence is basically I'm looking far and I look close by, so I kind of like bring my eyes close, and then they go far, and then they go close, and then far, so that achieves your 3D vision. And when they cannot do that, what our brain does, it comes up with an alternative strategies, like making a saccade. So if they cannot do this, then they make a little saccade, and then make another saccade, and then they adjust the two eyes in kind of a random way by combination of making a convergence and making a conjugate saccades. And so what we tried to do is we studied Parkinson patients, and we studied different kind of strategies that patients with Parkinson's use. And what it turned out, they frequently utilize saccades to make these 3D gaze shifts. And frequently that utilization of saccade is not as accurate, and as a result, they see double, they see blurred. So since over here we want to focus more on what will be future, I'm not going to present the data which is already currently in review, which is different strategies and whatnot. But for that strategy, we came up with a concept. And this concept was based on, of course, good old Robinsonian model. So what we had is so Dave Robinson and Lance Opticon, they came up with this model of convergence, where they had, this is just a little schematic, Palak will show you the real model, but the whole idea is that whenever there is a desired vergence, which is a command which is given to the brain by disparity or the blurriness, that disparity then goes to a black box, which is your vergence circuit, and that circuit executes certain kind of commands, which then leads to actual convergence signal, which moves two eyes together. So there is a little black box, which is your vergence circuit. And then, of course, in parallel, there is another circuit, which is a saccade circuit. So when your vergence is not optimum, your brain knows that you need to compensate by this much level of saccade, and then that signal goes to the saccade circuit, and then it makes an actual saccade, and together they make a gaze shift. So we did different types of strategies to simulate this, and one of the strategies that worked out the best is that one controller of saccade and vergence is the foveal error, right? So whenever I want to see something clear, the image needs to fall on a specific part of your retina, which what we call fovea, where their maximum number of photosensors are. And if there is an error in that image, then image is going to be blurred, and that error passes on to the brain, and then brain corrects the motor command to adjust the eyes so that the image goes on to the fovea. And then it gets fine tuning, and finally you get to the image. Imagine a camera, right? So when you're trying to take a picture, you have to adjust the camera lens. It's not quite that, but you know, you have to kind of get to the clarity. So it adjusts the eyes to get to the fovea. So that's one is the foveal model, which did not simulate all the eye movements that we wanted. So then we added another aspect to the model, which was omnipause neuron model. So what omnipause neuron do? So omnipause neurons are the inhibitory gateway of most eye movements, particularly saccades and vergens. So as I'm looking at the screen and I'm gazing at something, I don't want my eyes to move around. So what nature has done, they have given us omnipause neuron, which constantly send glycinergic signal, which inhibits any kind of eye movement. So whenever you lesion omnipause neuron or turn it off for a little period of time, then it triggers these all saccades or vergens or any unwanted or wanted movement. And when you want to volitionally make a saccade or vergens, your brain turns off the omnipause neuron for a transient period of time, and that's an opportunity when there is a burst of firing and saccade happens or vergens happen. So we added this omnipause neuron to the model. And what omnipause neuron works, it works as a switch between saccade and vergens. So there is an omnipause for saccades and omnipause neuron for vergens, and they act as a switch. And by having the switch, it either lets vergens operate or saccade operate. And what we simulated there is a noise into the omnipause neuron switch, and that noise then leads to combination of saccades and vergens that we saw in our Parkinson patient. And that noise in omnipause neuron comes from the outflow of the basal ganglia. So as you all know, that Parkinsonian state is a noisy state in the brain, right? So there is a perfect synchrony into the basal ganglia, which is our deep motor nuclei. And that synchrony, when it is lost, when there is a lot of noise into the basal ganglia, that leads to tremor, that leads to tone, increased tone, gait problems, slowness. But not only that, it also leads to a lot of noise into the omnipause neuron system. And then it leads to this combination of saccade and vergens. So what Palak did, that she simulated this model, and then it gave a lot of data that it had several a priori hypotheses, and we could get the data. So I will give this to Palak right now for her to go over the model. Okay.
Hi. So as Dr. Shaikh explained, the idea here was to understand exactly, like, once sort of the brain understood that it saw a target, and there was some internal calculation of how much the eyes were supposed to move. So that's what we're talking as delta V, or change in position or gaze shift. And so that was ideally what was supposed to happen in any normal person. But with Parkinson's, this circuit is compromised. So I'll explain now how that happens. The idea is, normally you would have this signal, which is basically a displacement signal at this stage coming in. And then this signal goes into three different components: the SVBN, the VVN, and that is then fed back into this signal with VVC. Now, what are all of these things? So this is a color-coded model, so I hope that'll make it slightly easier to understand. The idea of the omnipause neurons, or OPN, that we talked about earlier, the idea is that OPN controls what we call SVBN and SBN. So what do these stand for? They basically stand for saccade burst neurons and saccade related vergence burst neurons. So what the OPN is really doing inside of this circuit is every time there is, the OPN modulator is the source of this noise. So whether it gives the appropriate signal or a noisy signal into the OPN, that then controls the SBN as a switch and the SVBN as more of a gain factor than a switch. So the next block, the green block that I will point your attention to, is the vergence velocity neurons. And these neurons are the ones that are recruited in order to control the velocity of the gaze shift that the eyes perform. So basically what is happening in the circuit you see below with the SVBN and the VVN is the burst neurons and the velocity neurons are taking this gaze shift signal and turning that into the required velocity. That is what you would normally see as a vergence gaze shift, or basically a slow continuous gaze shift movement. The circuit on top is the saccadic circuit that includes the OPN controlled SBN. And delta C basically stands for the conjugate change in position, and conjugate movements are basically what we're terming as saccadic movements. They're basically also called conjugate movements. So the idea here is that the OPN controls the saccade burst neurons. So how it's doing that is the OPN acts as an inhibitor. So every time the OPN is active, the saccades do not occur, or they're suppressed. When the OPN is inhibited is when the saccade generation actually takes place. Now this would be applicable for, again, a normal uncompromised system. What we see in Parkinson's is that there is higher latency and lower velocities in the gaze shift. So the idea is, one, that there is noise in the OPN modulator, which leads to noisy inhibition with the OPN in both of these circuits. The other idea is that the brain is aware of the gaze shift that needs to be executed, but the execution is compromised. So the block here down below that says default is basically that idea that the brain is aware of the gaze shift that does need to be executed. So what we understood from our experiments and simulations was that the default system tells us the velocity that should have been maintained to perform this successful gaze shift, and the actual vergence circuit tells us the velocity that was actually sustained in real. So next is the comparator block that sort of compares these two velocities, and when this velocity is below a certain threshold, that is when the saccade the saccade circuit is activated. So as Dr. Shaikh mentioned before, that's when you see a combination of the vergence and the saccade that we see in people with Parkinson's. The rest of the circuit that you see here, specifically focusing on the yellow blocks, is basically, again, what you have the velocity that is coming out of this burst neurons in both circuits, and then there is a sort of an integration function that's happening internally, which then gives the actual gaze shift, that command that is then taken to the ocular motor plant. So we simulated, our model, and these were some of the simulation results we got using this model. As I said, as Dr. Shaikh said before, this model was sort of a model number 3 that we finally came up with, that the one that we found was the best at simulating this and had a realistic physiological basis to it. So talking about the simulations.
Palak, 1 second. Let me just tell them what was 1 and 2. So basically, model number 1 was original David Robinson's model, which had mostly the foveal velocity. And the model 2 was Lance Opticon, who was also Robinson protege. He modified the model to add OPN circuit to it. So what we did is we combined the Opticon and the Robinson model, and that was our model, which was a third model. And can you show them the OPN gain and Vergence velocity gain into the model so that they know what they're looking at?
I didn't understand you.
Okay, so I just wanted to tell them that, Vergence velocity gain over here and OPN gain over here, these were the different gains that we modulated here. So go ahead now.
Yes, so as I said, the OPN acts like a gain in the Vergence circuit. So I think that's what you were talking about. So our simulations were basically looking for 2 things. If you look at the third figure on the rightmost, those are actually those are actual eye movement recordings that we took from patients with Parkinson's. Those are the solid lines, and the dotted lines that you see behind them, those were our simulations. So as you can see, there is a very, very good fit using this model. So what did we consider while we were trying to fit these and get the optimum results was, 1, the OPN gain, and the other was the Vergence velocity gain. What that basically means is we were looking for a model and the model parameters that would enable us to match the velocity as well as the amplitude of the gaze shift. How we did that was, if you look at figure 1 here, that is on y-axis, you see the OPN gain. Those were the values we simulated. And on x, you will see the velocity gain. And so basically a combination of these values enabled us to get a good fit of the amplitude of the gaze shift that was executed by these patients. And the second figure shows you the appropriate velocity ranges that we simulated in order to match those that were shown by these subjects.
The other important thing that you may want to tell people is that, as you increase the OPN gain or velocity gain, both, you see the increase in the velocity, right? So as you can see here, either this parameter or this parameter, both increases the velocity. So if you look into this model here, then if you increase the OPN gain or the Vergence velocity gain, both of them improves the Vergence velocity. And of course, there is combination of OPN and Vergence velocity together is most effective in improving the amplitude. So now the next thing that we want to do is we want to know how we can simulate and what we can do to get better DBS results. So Palak, I will take them through the DBS results, and then we can get back to the model and we will open the stage for discussion. So what you are seeing here is this is the data of two classes of Parkinson patient. One Parkinson, so what happens when you implant the deep brain stimulator in the Parkinson patients, either that works for that patient or DBS does not change the versions. So these are two different classes. So on the left side, I'm plotting convergence or divergence position, and the x-axis is time, and the red is when DBS was off. So as you can see that in these patients, they are not able to make effective convergence or divergence. But in the same patients, when I turn on the DBS, they do a better job. And compared to that, when we have DBS off or on, in some patients, there is no change. So the question that we ask is like, how in the world we can explain that whether DBS would make a difference or it would not make a difference. In other words, how or where we can stimulate in the brain, then which can lead to a consistent improvement in convergence. And that's the question that we are asking, and that's what the future experiments are going to be about. And I'm just showing this model again, and we will start the discussion like, what should be our a priori hypothesis and how DBS can improve. So one way we can think about it is that if you somehow improve the vergence velocity gain or omnipause neuron gain, by increasing that gain, you can increase the vergence velocity. That's based on our model, right? That was our a priori hypothesis. So we want to have somehow the OPN modulator, which then influences the OPN gain and vergence velocity gain to improve the convergence function. So the question is, where is the OPN modulator into the subthalamic nucleus? Where is the OPN? And that's the area that we are looking at next. That's the experiment which we are doing now. And I guess that's and of course, the modulator, based on some pilot experiments, we think that it is the area of the subthalamic nucleus which then projects to the deep cerebellar nuclei, which is dorsal aspect of the subthalamic nucleus, which goes via pontine nuclei to the deep cerebellar nuclei. And these deep cerebellar nuclei have this VVN, vergence velocity neuron. They influence vergence velocity neuron. And also the omnipause neuron can be influenced by substantia nigra. So then it comes down to more ventral aspect of the subthalamic nucleus. So the question that we want to ask is that we want to create a probabilistic stimulation atlas and figure out that where in the subthalamic nucleus that we stimulate, which can then lead to modulation of this model. So currently what we have some clinical data which we are still analyzing, and we want to try fit that data into our a priori hypothesis and see which parts of the model explains the DBS induced change. So that's where we are at right now. And I tried to make it more of like more time for discussion. So I think we have about 15-20 minutes for discussion.
So thanks, folks. It's too bad that your neurons aren't color coded like your diagram here, so that you can find them easily. How do you said that those were going to be your next experiments. So what do you mean by an experiment?
Yeah, so what we are, I mean, again, in DBS world, it is very crude, as we had discussed this before. So what we are trying to do is we are trying to bring patient in on different occasions and turn on the clinical setting, which is on the dorsal aspect of subthalamus versus ventral aspect of subthalamus, steer current in different regions of subthalamus, and do the same experiment again and again, and find differences. So what really happens to behavior, in other words, the eye movements, when we stimulate the dorsal STN versus what happens when we stimulate the ventral STN. And then we do that in multiple patients. And ultimately we integrate different regions of volume of tissue activation to find a common trend. So hypothetically, I would imagine, if our hypothesis is right, if there is a consistent change in the velocity, that means this area is going to be quite activated. And based on non-human primate studies, we know that that area receives input from the deep cerebellar nucleus, which then is under control with the dorsal STN. So dorsal STN stimulation would then be quite well responsive to the efficient changes in the velocity. Let's say if we don't see a lot of change in the velocity, but if there is more only the OPN, which is more saccades, then it would be more towards more rostral, or it could be dorsal. So the experiments that we are alluding to is like we are going to stimulate at multiple different locations, because current data that we have collected, which Palak is currently analyzing, they are all clinical data. So it's not necessarily always dorsal or always ventral. It is clinically optimized. So what that means is that when patient comes to our clinic, we turn on different electrode contacts, and we just map out that which electrode contact is best for what we can see in our clinical setting, which is like most of the times it is increasing the tone, tremor, slowness, how they feel in general. And based on that, we come up with that parameter and that location, and we turn that location on. But what it does not tell us, that setting does not tell us that there would be a different locations on the electrode if we turn them on that can help with convergence, for example. So we want to find those areas in the subthalamus where if we stimulate, that may not necessarily give you the effect on tremor, but it can improve your convergence. And once we find that area, we can program the DBS lead in such a way that on sometimes it stimulates the tremor area, on sometimes it stimulates the convergence area, and then like we call interleaving, we can get best of all world. So that's what I was alluding to.
Are the sort of the contact, is the contact geometry sufficient for the kind of selectivity that you're looking
Yeah,
for?
no, it's a problem, of course, but that's the best we have right now is,
Sure.
all we have is DBS lead. I wish we would have much better stimulation, much finer stimulation interface than what we have available right now. I mean, the current lead size is 1.5 millimeters in most of our patients, and that's the best we can get right now, unfortunately. And of course, as you can imagine, the VTAs are quite large also. Let me show you an example of VTA here. So these are the volume of, this is the model that Cameron generated in one of the patients. I'm just giving you an example. So, so if you see that when the VTAs were more on the dorsal aspect here, and when it was stimulating some of the dorsal aspect of subthalamic nucleus, we saw some changes in vergence. And when it was not dorsal, when it was like more to the sides, it did not change the vergence. But as you can tell, that VTA size is quite it's little smaller than subthalamic nucleus. Having that said, like, of course, the electricity within the strength of electricity within the VTA also varies, right? So it is most at the core, at least as you go more towards the periphery. But based on what we know right now, or what we have available right now in the basal ganglia, we cannot selectively stimulate particular areas. So of course, that's one of the challenges.
Okay, questions from other folks or suggestions, comments?
So I think that's why I just wanted to add one more thing is doing non-human primate experiments. So we're working with Don Taylor and our colleagues at WashU, where we can, implant the DBS in subthalamic nucleus and simultaneously do single unit recordings from the cerebellum and see how they are modulated, the activity within the cerebellar nuclei are modulated because they drive vergence. So I think we probably will get more answers from non-human primate experiments as well, that we can then use that knowledge to treat our patients and apply that to the Parkinson's patients and DBS.
So that's one thing about recording from deep cerebral nuclei. But the other thing that Fatema is working on with Don is Don here? I don't know. What Fatema is working on with Don is they are trying to, I think they already set up the eye movement lab in Don's lab. So we have ability, right? I think they're working on it. And
we kind of were on a holding pattern due to COVID, but we'll get back.
yeah. So they are able to record monkeys' eye movements, and then with a single unit electrode, they can selectively stimulate different parts of the subthalamic nucleus more precisely than DBS lead, and to look at these behavioral patterns in monkeys also. So that is something that is going on, and is of course it's on our agenda, or Fatema's and Don's agenda.
So what do you guys need? I mean, what will it take to sort of figure this all out?
You mean in monkeys or in humans?
In general. So
Well,
the big picture,
Well, the big picture, I think what we need is like a better resolution of electrodes. And to be honest, I mean, we are making some progress. So now we have directional leads, right? The newer leads are directional leads. And with directional leads, we can be creative in making smaller size of VTAs, more selective VTAs in humans. My previous patients, I had most of them had old Medtronic lead. Now we have Boston leads, we have Abbott leads, and there are directionality there. So we can be more selective in stimulation in those leads. So we are already heading in that direction. And it's good to have that, because once we find a directional lead in a particular area which is responsive to vergence, then we can creatively program them so that we can control vergence and tremor from two different areas. But of course, if I have a wish list, if I can poke an electrode in somebody's brain and then keep it there in basal ganglia, that would be the best way to test it. But of course, it's not good for humankind because it's not. So of course, it's just. And of course, intraoperatively, one can do that. But the problem with intraoperatively is the frame setup is very tricky. So we can't really have a sophisticated eye movement measurements while they are in the OR alert. I mean, you can do some basic experiments, but not these type of experiments. So I think the best way would be to have more higher resolution leads, and hopefully in near future we will get there.
Okay.
And of course, monkey experiments would be very instrumental in telling us a lot. And we are putting grants to look for it. So we need some good reviewers also.
You mean at NIH or locally?
At NIH.
Not much I can do about that.
You know, like we put a big grant to Department of Defense, like looking at humans and then translating it into monkeys. And we had us, we had Don, then we had folks from WashU, and we had like people from Ludwig Maximilian to do like monkey anatomy experiments. We had like a nice dream team there. And then reviewer said that, oh, this is not an important problem in Parkinson's disease. That's it. But it is an important problem. It's just unfortunate. Sometimes it just goes in wrong hands.
Yep. Okay. Other questions? Suggestions? My suggestion is make sure that you write the importance of Parkinson's disease in your introduction. The importance of this in Parkinson's disease.
Yeah, so it is actually what happened is it was just matter of few months. So like 4 or 5 months after that grant was rejected on that excuse, American Academy of Neurology had a big press release about how bad the problem, eye movement problem is in Parkinson's disease. And it was like, it hit press everywhere. And that was like all over the place in American Academy of Neurology. So now like I just directly start with that press release. So people, it is very convincing for people. Before that, it was hard for me to say. They would say, oh, you are an eye movement guy, so it is important for you, but not for everybody else. But now American Academy of Neurology has made it very clear that this is important. So now we are citing that.
I have to confess that I thought you're an eye movement guy. Of course it's important to you when you were presenting this. That's all. I'm glad. I mean, you need to have some backup other than me, but okay. Well, thank you all. That was great. We have another one coming up next month, like I said before, Nathan Mikowski. So I'll see you then.
Thank you.
All right,
Thank you.
thanks. Have a good afternoon. What's left?
You too. Bye. It's nice outside.
Yes.